The broadcast is now starting. All attendees are in listen-only mode.
Hey everybody, welcome back to Young Engineers of Today. I hope you've all had a good week and I hope you're ready to continue with Learn to Fly. So we're going to continue with just a little bit more of aspect ratio. We'll give you guys, I don't know, like 15 minutes at the beginning of the class to finish doing the test flights. And then we'll get started on wing loading and go from there. So why don't we go ahead and go down here and you can go ahead and get X-Plane started up and load up your test planes. If you've already run the all of the test flights, go ahead and raise your hand. Otherwise, if you have not, then just go ahead and run your remaining test flights and then raise your hand when done. For those of you who already finished, it might be a little bit slow, and for that I apologize. I realize we're already off to a pretty slow start, but yeah, um, once we're done with that, we can look at the data and move on to the next lesson. For those of you who are joining, no, your speakers are not broken. It has been quiet this whole time. We're just doing test flights on aspect ratio, just finishing those up for the next like 10 minutes, and then moving on to the next lesson. And then just as a friendly reminder to raise your hand once you are done running the test flights. All right, we'll give it just a few more minutes. Since we seem to be split about 50-50 on people still working on it and people finished. Alrighty, let's go ahead and call it there. since we got just about everybody on board. If you haven't yet, that's okay. We take a look at the average takeoff trials graph down here. So we've got average takeoff distance in feet and wingspan in feet. And for those of you, you know, writing down the data and stuff like that as you go along, well, I mean, and really, you probably notice this anyway, even if you weren't writing down the data. But if we were to look at our graph here, where like wingspan in feet started at 10 and went to 50, and average takeoff distance was like 1,000 to, I don't know, well, let's say 5,000. I'm just pulling some numbers. There's nothing, really hard and fast about these. You might notice that over here, the longer wingspans, it takes less to take off, and then in the intermediary areas, it takes more. Some of the middle schoolers even found that it started to approach infinity because the plane never actually took off with a wingspan of 10 feet. You might find that as well. The chord might come a little bit too close to 1 to really have enough stability for the plane to do anything. Your mileage may vary. But yeah, you're probably looking at some kind of graph like that. Maybe not with the exaggerated arrow off into infinity. Generally speaking, though, it is easier to take the plane off with a longer wingspan. And to a point, this is certainly true. At some point, the wingspan becomes long enough that the plane becomes too heavy to take off. And as you increase the wingspan, you also sacrifice maneuverability and speed on the plane. It generates lift at lower speeds, which is nice, but it also can't react as easily and runs into problems with fuel consumption and things like that. So there's always a trade-off to be made, which is why they say that the ideal um, uh, is sort of in the mid of the 1.0 to 12 aspect ratio threshold. So as far as the investigative questions are concerned, as the aspect ratio increases, does takeoff distance increase or decrease? Well, we've shown that the takeoff distance decreases as the aspect ratio increases. Now, the shorter takeoff time, does that indicate more or less lift? More. I mean, pretty straightforward. You're taking off earlier, so you got more lift. So what are some of the advantages of higher aspect ratio? Well, looking at more lift. How could we increase the aspect ratio without changing the length of the wingspan? So how else could you change the aspect ratio of a plane? Well, okay, you could change the mean chord, right? Change this right here. Change the thickness of the plane wing, and that will change the aspect ratio as well. If you have not already, watch the landing aspect ratio video. That doesn't really exist. You will land your 10-foot wingspan airplane 3 times. Next, land your 50-foot wingspan 3 times, blah, blah, blah. So wing loading. That's actually the next thing that we're going to be working on is wing loading. So let's take a look at that. We learned that weight impacts takeoff performance. Actually, that was one of the sets of test flights, was where you guys took off with varying increasing amounts of weight and saw that the takeoff distance was longer. It might have actually been one of the ones that we didn't get to because we were trying to get to the engineering of flight, but regardless. Generally speaking, the greater the airplane weighs, the longer the runway needs to be. Makes sense. A heavier airplane needs to generate more lift, which generally requires more thrust, which generally requires a longer runway. Anyway, you get the idea. What do airplane designers do when they need to carry a larger payload but still take off on the same runway length? Interesting. All of these issues are related to wing loading. Wing loading is the ratio of the plane's gross weight, which is W, divided by the surface area of the wing, which is S. This is similar to density, except it uses surface area instead of volume. Density is, mass, uh, the amount of matter in a given volume. So we could say that, um, you know, fog is denser than clear air because there's water particles in there and stuff like that, and water molecules, I guess, is the more correcter thing to say. So you've got water molecules in there, so there's generally more stuff inside of a given sort of cubic foot of air. So the air is denser. Heavier metals, uh, like if you've got lead and you've got, I don't know, aluminum, lead would be the denser metal because with the same amount of, like the same volume of lead will weigh more than the same volume of aluminum, which means that there's more matter in the same volume of lead than there is in that volume of aluminum. So lead is denser. So this is very similar to density, except it uses surface area, not volume. This ratio is actually a very important concept in designing airplanes. Let's investigate how changing the wing loading of our airplane impacts flight performance. We will begin by using the most important tools of scientists and engineers, critical thinking and math. What a letdown, right? No, but it's actually very useful. So we will increase the wing area of the plane to see the impact on wing loading. Listed below are different wingspans with the same length chords. Please calculate the wing loading for each wingspan. Please pay attention to the trend. Feel free to do this on a spreadsheet or use a calculator. So let me go ahead and get my calculator open. Calculator. Doot, doot, doot. All right, so we've got our gross weight, which is in pounds. We got our wingspan feet, which is in 50. We got our mean chord feet, which is in 5. I totally messed up the last two parts of that, but that's okay. We got our gross weight, which is in pounds, and our wingspan and mean chords, which are in feet, 2,500, 50, and 5, respectively. So first things first, we need to, so in order to figure out the wing loading, it's pounds divided by fared. Oh my God. Feet squared, right? So we need to figure out the surface area, which is in feet squared, which means that we need to multiply the wingspan times the mean chord. So 50 times 5 is equal to 250. And let me just go ahead and write that in here, 250. And then if we're just to do some real quick math, 2,500 divided by 250 is 10. So the wing loading in this case is 10 pounds per square foot. Each square foot of wing is responsible for having to lift 10 pounds of weights. Not bad. Now we've got wingspan, mean chord of 40 and 5 respectively. So let's say 40 times 5, that's going to be 200. And so 2,500 divided by 200 is 12.5. So we've got 200 and 12.5. And let's just solve out these last two. 20 times 5 is 100. 2,500 divided by 100, to nobody's surprise, is 25. So 125. And finally, 10 and 5. 10 times 5 is 50. Yeah, we're going to get that. 2,500 divided by 50 is going to be 50. Oops. Go back to the pen. So 5, 0, and 5, 0. So the trend we've got here is that, let's stay like that for now. As the wing surface area decreases, the wing loading increases. And that's because the weight of the plane in this does not change. So if the wings are smaller, the weight is distributed along the wings more heavily. So again, to put it into the terms that I was speaking of before, with a wingspan of 50 and a mean chord of 5, that gives us a wing area of 250 feet squared, which means that each square foot of wing is responsible for lifting 10 pounds of plane, which means that the work on the wings is easier versus 10-foot wingspan with 5-foot mean chord gives us an area of 50 square feet, which means that each square foot of plane wing is responsible for lifting 50 pounds. Each square foot of plane wing can almost you can almost think of it as like a gremlin or an Oompa Loompa or something like that trying to lift something up. They're going to have an easier time lifting 10 pounds than 50 pounds. Same goes for plane wings. So the wing loading versus the wing area, if we were to graph this out, you'd be looking at like 250. Well, actually, what am I doing? Why don't we start at 50, like sane people, and then go up to 250. And then we'll start at 10 and go up to 50. And we'll be looking at a graph that, as it stands right here, pretty linearly decreases. So as we increase the wingspan, we decrease the amount of work that the wings did, each sort of section of area on the wings has to do. Now, please calculate the wing load when the wing area stays constant and the gross weight decreases. So now we've got a wing area of 150 feet and a gross weight of 2,550. So all we do is 2,550 divided by 150 square feet, which gives us 17. And then we've got 2,250 divided by 150, which gives us 15. I know this is all terribly thrilling right now. And then we've got 1,750 divided by 150, which gives us 11 2/3. We'll say 11.6. And 1,500 divided by 150, which is going to give us an even 10. So as the gross weight decreases, the wing loading also decreases. I mean, that's pretty obvious, right? Like, you don't need me to explain that to you. As something gets lighter, you have to do less work to lift it up. Baby stuff. But anyway, so as the wing area increases, does wing load increase or decrease? As wing area increases, wing load decreases. We saw that. As the gross weight decreases, does wing load increase or decrease? Wing load decreases. We saw that. Fighter aircraft usually have a low aspect ratio. If we increase the payload of the fighter aircraft, will the wing load increase or decrease? So as we saw, as the gross weight decreases, wing load decreases. If we don't change the aspect ratio or the wingspan of a fighter aircraft, we aren't changing the surface area of the wing either. So if we increase the payload, we're increasing the gross weight, which, by extrapolation means we're going to be increasing the wing load. So our small private plane carries 6 passengers. The plane weighs 2,900 pounds. The wingspan is 34 feet and the chord is 4.75 feet. 47.5 feet. The plane does not take off. What is the wing area of the plane and what is the wing load? Well, let's do some quick old math here. All right, so we've got a wingspan of 34 feet. We got to multiply that by the chord of 4.75. Boom, that's 161.5. 2,900 divided by 161.5 is 17, almost 18. So the wing load is roughly 18 pounds per square foot. The wing area of the plane is, what is it? About 161 square feet. Math. The wing load of our plane is 15 pounds per square foot. The chord is 5 feet and the wingspan is 30 feet. What is the gross weight of the airplane? Okay, so this is everything but just in reverse. So we could do this one of two ways, depends on what makes more sense in your mind. If it's pounds per square foot, LBS divided by FT2, little 2, that's almost like saying LBS divided by feet times feet. Because feet squared is nothing more than feet times feet, right? So we can turn this into that. Now, if you want to, let's say, pounds per foot, if you want to just get the pounds in this case, we'd have to do the opposite in order to take away the foot, right? So we'd need to multiply this by feet because it would force the foot and the foot to cancel out, and we'd just be left with pounds. So we can do this one of two ways. Either we can multiply the pounds per square feet times square feet, or we can multiply it by one of them, one foot dimension and then the other foot dimension. So let's try both of them. Let's say 30 times 5 is 150. So if we take 15 and multiply it by 150, we arrive at 2,250, right? And then just as a proof of concept, 15 times 5 times 30, look at that, 2,250. I know, please, try and contain your enthusiasm. But yeah, so that's just, there you go, two ways to think about it. All we're looking to do is we're looking to get the feet out of this equation so that we just have the pounds left over. I know. I am building a plane that will weigh 8,000 pounds. The wing load is 17 pounds per square foot. What's the wing area? Oh boy. All right, so now we've got the opposite problem. So we need to know, we've got 17 pounds per square foot, foot squared. There we go. And we need to turn it into feet squared. So we're in a bit of a predicament here. What is going on right here? So that's going to be square feet. So we need to figure out how exactly we can get to this. So we can do a little bit of math trickery here. So 17 pounds per square feet is the same thing as saying 17 pounds per 1 square foot. Those two are equivalent. What we want to do is we want to get rid of u and be left with u, and we've got 8,000 pounds. We've got u. So we need to figure out how to get this away by using this. So we can use the same trick that we did before, kind of, because we can't really multiply into it yet, but we can make it so that it's possible to multiply by just flipping it. So if we go 1 foot squared times or over 17 pounds, and then we multiply it by 8,000. It's the same thing as 8,000 foot squared pounds divided by 17 pounds, which is going to cancel out the pounds. So all we need to do in this case, 8,000 divided by 17, and we arrive at 471 square feet, which is roughly in keeping with everything considering. So yeah, I mean, you guys get the idea. The wing load of our plane is 20 pounds per square foot. The gross weight of the airplane is 2,400 pounds, and the chord is 4 feet. What is the wingspan? Well, it's just different permutations on the same idea. So let's actually get to the experimentation point. Let's open up our plane maker. And we're going to open up that RV-10 aircraft that we're so fond of dismantling and messing with. So RV10.acf. We're going to open up that aircraft, and here it is. Look at it. Look at it. Look at it flipping. Anyway, so we're going to save the file 3 times with the following 3 names: name WL15, name WL30, and name WL60. In this case, name would be replaced with your first name. For example, if your name is Terry, then you would save RV10 as Terry WL15. Thrilling, I know. So yeah, basically what we're going to do is we're just going to go ahead and save as, and let's see here. So this is going to be Thomas WL15.acf, save, and then save as Thomas WL 30 and 60. So 30.acf and 60.acf, and boom, we've got our 3 saved planes for modification. So let's go ahead and check that out. So make sure to open up one of these that you just saved. So we're going to modify name WL15 first. You don't have to open it up like this, but it's just good to make sure that you've got like the right plane for the situation. So select standards, click on wings, and modify the wing of each plane according to the table. So for WL15, the weight is going to be 2,500. The chord feet, we've got a couple of chords. Well, all right, so the wingspan, the semi-length is going to be 7.50. All right, oh, there it is, okay. 7.5, and then the wing to lateral arm is going to be 7.45, and the vertical arm is going to be -0.85. And so if we were to go back to our plane, we can see we've got these little short, stumpy wings. I feel like this is backwards. Oh, this is not weight load 15. It's weight load with a 15-foot wingspan. Okay, there we go. So yeah, we got our little tiny wingspan plane. And then we're just going to go ahead and save. and then open up 30. Oops. Open up 30. Do the same thing. Wings, semi-length is going to be 0, 1, 5, 0, 0. Wing 2, lateral arm is 14.95, and vertical arm is -3.5. Boom, done. Save. Open 60. And I think you get the idea. Wings, semi-length is going to be 30. Wing 2, the lateral arm is going to be 14.95, and the vertical arm is going to be positive 0.55. And hit enter, and we've got our 60-foot wings. Wait, no, that's not right. I did something wrong here. Oh, that's not, it's 29.95. There we go. Now it's on the ends. Cool. And we've got our 3 planes. Save all 3 of them, and then open them up in X-plane. So if we were to check out the extra aircraft here, an experimental, and then the Vans RVs, and then the RV-10, you would have your planes here. I need to reopen X-plane because for me it doesn't cooperate very well unless I reopen it. Normally you should be able to just go back to the aircraft selection, but not so for me. So anyway, let's spend the last 15 minutes of the class just doing that, and then we'll go ahead and do question and answer time, and then leave it open for all of that business. So yeah, go ahead and we'll get to it on that. If you end up finishing running the test flights, because what you want to do is you want to do just like the aspect ratio, where you want to get the distance traveled and see exactly how long it takes to take off with these different wing loads. So go ahead and test the different wing loads, do 3 takeoffs with each one, see how long it takes you to take off, and then we'll go from there. And again, don't forget to raise your hand when you're done running the test, just so I know, just in case we ended a little bit early. Also, I'm going to pause the screen on the table so that you guys have the appropriate dimensions for each wing. Oh dang, I got somebody who's real fast with flying. Or they got a super fast computer. I know it must be exciting just to sort of listen to me say nothing. Just uh, just do it for a few more minutes, and then we'll call it a class. Okay, so at this point, I know not everybody's done. That's fine. You guys will probably pick it up again on Monday, and you'll go from there with Mr. Dubik, probably finish this up and then go into another concept, and we'll repeat this until we get it done, probably sometime in the next couple of weeks, I want to say. Anyway, and then from there, who knows? We'll see what happens after that. We might be close enough to the end of the semester that we start doing the end of the semester wind down. We might have like one more lesson that we fit in there before the end. I don't know. Life's full of surprises. Anyway, um, regardless, that's going to do it for today. I'm going to go ahead and do the poll questions, and then if you have any questions about anything, I will be here. Otherwise, you will more than welcome to head out after the poll questions are done, and have a wonderful weekend, and we will meet up again next Wednesday. You'll see Mr. Dubik on Monday, obviously, but I'll be talking to you again next Wednesday.